In this video, the other temperature effect we're going to be looking at is the effect of temperature fluctuations and how this would affect absorption versus emission spectroscopy. So before I go into the calculations and discussion of this, I'd like you to pause the video and think about, for absorption, atomic absorption spectroscopy versus atomic emission spectroscopy, for which one does it matter more if the temperature of our flame or atomization source, whether it's ICP or flame, which one does temperature fluctuations matter more for, absorption or emission? All right, so go ahead and pause and think about that and come up with an answer. Okay, so I'm not going to answer the question quite yet. We're going to go through some calculations to see what's true. Okay, so let's go back to our sodium example. Our first excited of sodium. We already calculated n star over n naught at 2500 Kelvin, and we got a value of 1.15 times 10 to the minus 4. Okay, now what if that temperature changes? What if we go up to 2510 Kelvin? Right, so the temperature in our flame changes by 10 Kelvin, a very reasonable number. Like, this is probably going to happen. What is n star over n naught if we do that? We can plug in the values using the exact same formula we had before. The only thing that's going to change is the temperature. And we get 1.20 times 10 to the minus 4. Okay, so let's think about what's our difference in the excited state population. All right, so the difference in our relative population is the difference here. So we get 1.2 times 10 to the minus 4 minus 1.15 times 10 to the minus 4. Let's take that as a fraction of our 1.2 times 10 to the minus 4. Okay, and that equals 0.04, or about a 4% difference. Okay, now for emission spectroscopy, we're looking at this, right, this would be a 4% difference in terms of our signal that we get, right? Because we're looking at, again, we have our flame, we have our atoms. We're looking at the light coming from these atoms, and the light is directly dependent on how many atoms are in the excited state. So a 10 Kelvin change leads to a 4% change in the amount of light. And that is a change in light that is not directly related to the concentration of our sample, right? There wasn't any extra atoms in there. It's just that we have more, a higher temperature. So, a pretty significant difference, even with a fairly small temperature change. What about the ground state? All right, so let's imagine we only have, then this isn't true, but let's imagine we only have two states, right? We only have the ground state and the first excited state. There are other states as well. So the amount of molecules in the ground state is going to be 1 minus our fraction in the excited state. And we can take the difference between that and we can take those two, and we'll divide it by, again, our what's happening. We'll do this as a percentage. All right, and this is equal to 5 times 10 to the minus 6, or 5 times 10 to the minus 4%, or let me just rewrite this as 0.0005%. Okay, and so so this is, again, for the excited state, we're thinking about our emission spectroscopy, whereas the ground state, we're thinking about our absorption spectroscopy. The fraction of atoms in the ground state matters in terms of how many are there to absorb the light that's coming from our lamp, from our light source. And so we get basically a negligible difference here. All right, so difference in the amount of absorption you're going to get of 0.0005%. You're going to have bigger effects from other things happening in your sample than this. So even a 10 Kelvin change leads to very small differences in terms of the absorption. So this is, again, since this is the ground state, we're thinking about molecules going from the ground state to the excited state in terms of absorption. So the effect on absorption is negligible. The effect on emission is pretty big. And so what we see here is that for emission, a steady temperature is really important. Whereas for absorption, it's not as important. But a steady temperature is really important for reproducible results. And of our atomization sources, ICP has the most reliable steady temperatures, just with the way that the that plasma is formed, whereas a flame has pretty large temperature fluctuations. So emission really likes ICP. Emission is, I should say, really likes ICP as an atomization source because you get both high temperatures and more steady temperatures. So almost all atomic emission spectroscopy is done with ICP because you have both of these temperature effects working in your favor for ICP versus other atomization sources. Okay, so that concludes our little section here about temperature effects. The next thing we'll be looking at is line widths and measuring how we actually produce light. So here we're going to get to talking about hollow cathode lamps.